Today, we would want to spend some time on distributed computing fundamentals with the Hadoop and Spark. I want to stress the word fundamentals. I know, these technologies are very famous nowadays, and people jump on to, start building things, and they get frustrated where to start, and there are so many things available. But with that, also different challenges in terms of choosing the right technology for the right problems. So that's the talk today. Before that, I would quickly introduce myself. My name is Praba Santhanakrishnan. I am a data scientist in Microsoft Windows operating system teams. I've been working with Microsoft for the last 16, 17 years in various divisions, and currently working with Windows. We use these technologies on a daily basis to solve many of our complex problems. That's where a lot of my learning comes from, and I wanted to discuss with you today and what are these technologies and what opportunities that we have. And we will be spending a bit of time in Hadoop and a lot of time in Spark. I'll tell you the reason why we want to do that way. In fact, somebody asked me, hey, is Hadoop dead or dying? My answer to that is that it depends on how you see it. And hopefully we'll find that answer at the end of this talk. So a little bit of an introduction to distributed computing. We will spend some time on Hadoop MapReduce, which is the fundamental for all the things that we are talking about in parallel computing and using cluster, especially in clouds. Internals of Spark, especially the data object called resilient distributed data sets. And also we'll spend Spark data frames. That's the most famous now everybody is using for distributed computing, right? So the scenario is different, compared to maybe a decade or a couple of decades ago, and when we had the internet and we started moving away from client server to web. The data that we used are not in the large sizes, and the challenges that are pretty much solved using some of the relational database systems, and maybe the console from your desktop or a web, we're able to connect to the database and do the transactions, and pretty much we were able to do the business. But today's world are different. You get data from different sources, different varieties. Like who would have thought, there are so many billions of IoT sensors today sending the data, and we would need that capability to ingest the data, process the data, and get some insights from that to make some business decisions and continuity and things like that. Like similarly, web pages, like there are millions and millions of web pages today out there, and we could collect unbelievable amount of insights from all the content out there. So to process, to analyze, to gain insights, the typical the architecture that we had in the past using even the supercomputers and single platform was not really capable of doing that, and that's where the distributed computing came into play. In fact, theoretically it was there, but it was all made possible in practical because of the cloud capabilities that we have. All the big companies like Google's and Microsoft of the world started working on this, and finally the technology or the platform or architecture called Hadoop came into a mainstream, very famous when it comes to distributed computing. And there are more advanced technologies which are based on the Hadoop MapReduce framework paradigm is in play now. That's primarily Spark is the most famous one, and we will get into that in this conversation. So let me motivate with a small problem statement when it comes to distributed parallel computing. What you see on the screen is a Python program. I think Python is very famous when it comes to these kind of architecture. When you are working with the distributed computing architecture, whether it is in Hadoop or Spark, for that matter, any of these technologies. This is a hello world version of distributed computing problem statement. So all we wanted to do is we have a doc string, which has like 4 or 5 lines, and we wanted to find the number of times each word occurred in this string. Right, so that's the simple hello world example. So if this is what we have, I'm sure that we can write a quick Python program and run it on your single computer and then be able to find out very easily, very quickly, no issues. But if you were to do that on millions of web pages that are available today, single computer will take forever, or it may not even work for that matter. So that's where the distributed computing paradigm is in a big play when it comes to running these program or writing this program and running it on clusters of computers so that you can get things done in parallel. So when it comes to the parallel computing, you might want to think about like buying or securing the commodities of server, which are the nodes which are like may not be high-end machines, but I can submit my job, I can submit my data to it so that it can get the things done in parallel and get the answers at the end. So that's where Hadoop came into a play. You might want to you might ask, like, why do I want to count the number of words in a given text or a file or an internet page? Well, that is a primary base algorithm for a page rank algorithm that Google started with, and that's what made Google search engine really, really famous. And they were able to do that by getting the data from all the web pages in the world and getting the content. And when you do a search, the search relevance and the page rank and all those things are like pretty much built on top of these algorithms using 1 gram, 2 gram, or n gram from the text that available in these pages, right? So so this is an example in this case, like, we are just doing a count on the number of lines and the words in these lines. The Hadoop MapReduce is the paradigm, the architecture behind all these things, made it happen when Google started it. And then, of course, Yahoo picked it up from there. And then during the time, like Microsoft and Amazon and all the companies were working on this problem, but Hadoop became the most famous standard framework for these kind of problems. And in fact, that was open license through Apache. And now every cloud providers like Amazon and Microsoft, Google, IBM, they all provide this service. And Spark is the most advanced version from that, which is based on the MapReduce framework. What is MapReduce framework? You see this in this diagram. On the left side, you have a HDFS. It's some sort of storage. It's a Hadoop file system, which is part of the Hadoop overall umbrella. You have this mapper. The mapper, consider them as individual nodes. They take the data from your storage and they kind of create a key value pair. Key value pair is like, if you're familiar with Python, dictionary is a good example, or even a JSON file is the key value pair that you can relate to. So these mappers will create this key value pairs, and they're all in a different partitioning, and each key will go into one of these partitioning. Then there is a sorting and grouping that happens as the next step, and then the reducer will pretty much do the aggregation of this key value pair that is generated, and the end result is again going back to your storage or any sorts of display that you want to do. So that's a fundamental idea of a MapReduce paradigm. You start with the data on the left, you have a set of mappers, and they do mapping of each keys. I'll show you with the example what they do, then it will make much more sense with an example. So here is an example how the MapReduce works. We took that text which we saw in the first screen as part of the Python program. All we are doing is to count the number of times each word occurred in this text. We call that as input documents, and we map it. Our mapper function basically maps each line in this case. For example, in the first line, you see Chinese, Beijing, and Chinese. Our mapper function just maps each word and gives a counter. In this case, it's 1. And it does it for all the rows or all the text in the input side. And we do a shuffle and sort in the center. Basically, we group them according to the key. The key is that word, and the value is the counter, integer counter that we have. So Chinese, Beijing, Chinese are the words, which are the keys, and the number 1 you see on the right side is the value. So basically that's the key value pair that gets generated. Then you want to group them according to the key. So in this case, Beijing is in one key, and Chinese is another key, and Japan is another key. So you group them according to the key. And all our reduce function does is, doing the sum for based on each key. The key thing is that it all gets done in parallel. Of course, the example that we are using is a toy example, and you're not going to see a difference in or need to run this in parallel computing infrastructure. But if you are doing that for millions and millions of web pages, and you want to do this activity, the exercise, it does make easy to parallelize them. So the idea is that your mapper function and the reduce function, it's basically built on top of the functional programming, if you're familiar with that. For any given same input, you will always get the same output. So that's the fundamental of this. You will not have any other dependencies built into this function, so that it can be easily parallelized. So each mapper will completely run on an independent set of the data as the input, and it doesn't depend on anything else, so it can be easily parallelized. So that's the fundamental of the key value pair that you generate, and you aggregate them as part of the reducer. So that's the MapReduce at a very high level, actually. So you could have as many mapper, you could have as many reducer. It depends on your scenario, and you can add more nodes and more partitions in terms of how much is your load, and we can generate this, the output the way we want it. So in this case, we have in the previous case that we have a single reducer, so you get everything aggregated into the final reducer program. Here you have a two reducer where some keys goes into one of the reducer, the other keys goes into the other reducer. So everything else is same. So as I said, like, you can have as many reducers in parallel, but the key is to make sure that you have the mapper and the shuffle sort that happens right after the mapper that groups them based on the key. So that principle stays same. Reducer, having more reducer will reduce the time, but again, there is a balance that we need to do in terms of how much data you want to shuffle around between the nodes, because every time you shuffle the data between the nodes, it's going to cost you the IO. That's going to slow you down. The benefit that you get from parallelizing will not be lost by having more shuffle going on. So that's the fundamental. So we kind of talked about this concept that hey, it's based on the functional programming, where for a standard same input, you will always get the same output. So they are not dependent on anything else. So it makes it easier for you to parallelize them. So the map does not need to know anything about any other mapping task. Similarly, the reducing task or the reducer function, it'll have everything that it needs to reduce or aggregate the data that is coming in. Okay. So high-level architecture, how Hadoop does it. If you look at Hadoop, I would look them into divide them into two major components. One is the HDFS layer and MapReduce layer. HDFS layer is the Hadoop file system, and it's kind of like, you see the top half as the compute platform and the bottom half is the storage platform. Interestingly, both are distributed, meaning like the data gets stored in different nodes. At the same time, the job, which is the compute part of the Hadoop MapReduce is what we call. That's what that's also get distributed into the different nodes. You have the architecture of masters and slave nodes. So when it comes to distributed computing, you will see that framework of master node and the slave node. So in the MapReduce layer, you have a job tracker and the task tracker. And in the HDFS layer, you have a name node and the data node. So name node is kind of a master, and data node is the slave nodes, where it keeps copy of all the distributed data in the cluster. So to answer our first question, like, is Hadoop dead or dying? So I would say that the top half, the MapReduce layer, that is being kind of revamped, and there are many other technologies, even through Apache, Flume, Flink, and many other architecture coming in play. And Spark is the distributed compute, which is more standard when it comes to compute. But at the bottom layer, your HDFS architecture is pretty much still available, and everybody still relies on them, even though there are many other storage technologies, platforms provided by Microsoft, like Azure Data Lake and Amazon S3 and Google BigQueries and things like that come into a play, but they kind of share the same architectures, the principles of master-slave distribution. A little more detail on HDFS architecture. So you have the name node at the top, and the yellow boxes are the data nodes. So one of the challenge with the distributed computing is that we are leveraging the commodity servers, which may not be powerful, in terms of the storage and the compute power, but the collection of them together, what it really makes the difference. When you have a cluster of nodes, the chances of something failing is very high. So there is a concept called replication. So every time you write the data into a block of unit into any of these nodes, there is that the framework itself replicates into different nodes of the copy of the same data. So if one node goes down, let's say there is a hardware failure or a network failure or any other reason, if it goes down, so you always have the copy of the same data somewhere else. So we know that where to get that copy, and we'll be able to continue our job when there is a failure scenarios like that. How will I get a Hadoop MapReduce? So if you've not used it before, I would say start with some sandbox environment from Hortonworks or a Cloudera. In fact, there is a Docker version, containerized version available. You can go to Docker Hub and search for Hortonworks and Cloudera. These sandbox pretty much run on your single machine. They kind of fake the cluster setup behind the scene. For your learning purpose, development purpose, you can start from there. And once you get comfortable, I would recommend you can look into some of these clusters that are provided by the major cloud vendors like Microsoft and Amazon and Google. So Azure HD Insight is the Hadoop. It provides Hadoop and Spark clusters. So, and there is Azure Databricks. Databricks is kind of started from UC Berkeley. In fact, Spark was originated from AmpLab in UC Berkeley, and the Spark inventors formed a company called Databricks. So that is also provided through Azure, and that's like once you are comfortable with how your distributed computing works, and writing a program for which runs on your single computer requires different learning, different skills. but at the same time writing a similar or a same program and to run on a distributed cluster requires completely different mindset and approach. So we'll see some of those things in the next few minutes. So how do I I got my Hadoop set up, and the instructions are there in, if you look into Hadoop Apache web page or Hortonworks or a Cloudera, if you're downloading Sandbox, or if you're going with the vendor, a cloud vendor, there are a lot of documentation on how to get started in terms of setting up and things like that. So, okay, now we set up that Sandbox. I wanted to run this example that we just looked at it. There's something called Hadoop Streaming Job. Hadoop Streaming Job, it has a jar file. It's written in Java. Just by looking at the syntax, you can tell that. So all we are saying is that we need a reducer, we need a mapper, and there's something else called combiner. I'll talk about in a bit. We tell the Hadoop jar streaming job, this is what my mapper is, this is what my reducer is, and go get my input file, which is in part of the HDFS distributed storage, and you point the share name and the file name, and I would want the output file in this directory. And in this case, we are just choosing number of reduced tasks. And the mapper would be based on the partitions and the partitions in the nodes, and it automatically, Hadoop knows how many mapper it needs to create based on that. So now let's look into how does this mapper function and reducer function look like. So we are using Python. Python is very simple and easy to learn, and it is powerful and flexible. You could use Java as well. When it comes to Spark, there is something called Scala, which is the new language. In fact, Spark was written in Scala, so there are other options available when it comes to Spark. So pretty much Python does the job for you, and there are some limitations. We'll talk about it when we talk about Spark. So this is our mapper function. Simply, we are reading each line from the file, and we are emitting key value pair, and basically the word and comma 1 at the bottom of the screen that you could see. And the reducer function, which reads that stream that is generated by the map. The sorting happens in between the mapper and reducer, and you don't have to do anything specific unless you want to rearrange the sorting order differently. But the reducer will be able to pick up the stream that are coming in from mapper, and will be able to reduce that in terms of what we are trying to do in this case is basically the number of words. That's a simple example. Again, this is a very basic hello world example of how Hadoop MapReduce framework works. Now that we've gone through a little bit of Hadoop MapReduce, I wanted to introduce Spark. Spark is as I said, is the most famous distributed computing platform available today. Many of the leading industries, in this business is, as I said, like Microsoft, Amazon, Facebook, Google, everybody leverages Spark, and it is very powerful when it comes to doing these things in parallel. The key difference between Hadoop and Spark is like Spark still relies on this MapReduce framework. But the thing is that it does everything almost in memory. In fact, everything in memory. That's the power that comes from, because in the case of Hadoop MapReduce framework, so whenever you do the mapping function, the output of that goes into the disk again. Then there is a combiner function, which kind of does the local aggregation inside each node, and then it writes to the disk again. And then there is a shuffle and sorting happens. And then finally, the reduce function runs on top of the data. So there is a lot of disk I/O happens during the entire stream of the execution. That really, is the big bottleneck, because when you are talking about terabytes and petabytes of data going back and forth, writing back and forth into disks, it slows down things drastically. So that's what Spark at a higher level aim to solve, to in fact doing everything in memory. It kind of leverages the memory from the commodity server that we talked about. So assume that you have a large memory, which are collection of individual independent memories that are available in each nodes, and the execution runs on leveraging all the memories put together. For example, you create a object in Spark. In your code, it appears that it's just a single object, but behind the scene, the data for that object comes from different nodes in your cluster. But in your code, it doesn't appear that way. But that's the power of the Spark that comes in. That improves the performance drastically. I would say like 100 times in typical workload that I have seen between Hadoop MapReduce job and Spark job when you're processing, let's say, 10 gigabits of data. So let's get into some details in Spark. Spark architecture, it again, for like any other distributed computing framework, it has a master-slave approach. In here, we call a driver program. In Hadoop world, we call the name node data node. Here, we call it as a driver program, which is the kind of runs as a master. And then on the right, you see a worker node. The worker node, that's where the job gets executed. It also has the cache, and we kind of can leverage cache at times to speed up things. Just ignore the cluster manager in between for a minute, and then we'll come back to it in a couple of slides. But the idea is that you have the master-slave architecture here as well. The thing called Spark context, that's the kind of gateway to your cluster. So everything happens through Spark context. So once you have access to the Spark context, then you have access to the clusters where you can upload your data into it. You can send your program or the compute that you want to execute on each of this worker node and get the results back. So it's basically the key to the cluster. Again, we kind of touch base on this Hadoop versus Spark world where everything happens in Hadoop, going back and forth, writing back and forth between the operations into disks, and that's kind of puts the bottleneck. But in Spark, we do it in memory. How does Spark program looks like? This is again using Python. You can use Scala. So when you use Python in Spark, we call Python PySpark. You could use a Jupyter notebook, especially when you are learning or developing, building something, and you want to quickly test everything you're written and then see if it works. Jupyter notebook is fantastic. It works beautifully. In Azure, you will get Azure Jupyter notebook where you can have access to the cluster and you can write all this in Python. And of course, as we discussed, the Scala is also available. And once you're comfortable with your Jupyter notebook, everything works fine, then you might want to schedule that as a job, and that's when the Spark submit comes into a play. When you submit a job or when you are executing your Spark commands, you get access to Spark UI. That's basically, if you are running it on your local machine, you will have the local host on the port 4040 where you can see the status of the task. At the bottom, we have something called myRDD, and SC is the Spark context, which gets generated from the previous command. Parallelize range 1,100. So I'll just give you what happens if you execute this command, what happens in the background. All we are doing is generating 100 numbers, actually in this case 99 numbers. In Python, range 1,100 is 99 numbers, 99 integers it generates from 1 to 99. And we say it's parallelize, and then we create something called myRDD. myRDD is a resilient distributed data set. It gets created as a one object for us, whether we are writing in Jupyter or in a Spark Submit program. But behind the scene, these 99 numbers that gets distributed based on the number of nodes that you have. Let's say you have 4 nodes in your cluster. These 99 numbers or 100 numbers, for the sake of discussion, 25 each will get distributed to the 4 different nodes. Just a simple example how the data gets distributed, but the real benefit is that when you have terabytes, petabytes of data, And again, it gets distributed based on the number of nodes and the number of cores, the CPU cores in each of these nodes. So that's where the parallelization comes into a play. It gets done automatically behind the scene by Spark executables. How can you run Spark in different modes? You have the local at the bottom. We'll go from bottom to the top. Local is everything happens on a local computer. It's great for learning and debugging. There is no cluster manager. Every parallelism is limited to the number of cores in your local machine. Again, like when you start with the sandbox, that's where you would start. And there is a client mode where code resides on your client machine, like maybe your desktop, your laptop. Outside the cluster, basically your client acts as the driver. It's very good for development purposes, where you want to see immediate results and debugging, investigation, making sure that there are no bugs and you can fix everything. Once you're comfortable with that, that's when you go to the fully cluster mode, where you submit the job, your master or the driver node is also in cluster, and your worker nodes are also in cluster, that everything runs isolated and you get the results stored in a destination data source. Coming back to the architecture again, the cluster manager is in the center. So you have different options, especially when you are running in your cluster in whether it's in cloud or on-prem. There are many options that you could use as your cluster manager. So you will see standalone. That's like when you do a sandbox, that's what you get. Then Apache Mesos, Hadoop Yarn, and Kubernetes are the other options. The most famous one is the Hadoop Yarn. It's used in your Hadoop MapReduce clusters and as well as Spark. And Yarn is again a standard when it comes to cluster manager for any of the distributed computing today in any other architectures that we see. So basically, your driver program connects with your cluster manager. The cluster manager, in this case, let's say Yarn. Yarn manages your cluster. It knows how many nodes are there, how many cores in each nodes, and which one is available, which one is resources are blocked, and or which one is healthy, not healthy. So it kind of manages all these things for you. When a driver program asks for resources and the cluster managers gives you the details back on what nodes are available, then the driver program sends the program and the data, and then that gets executed. So that's the role of the cluster manager in between. Kubernetes is an interesting play in here. It's kind of started as a container orchestration. It can be used as the cluster manager as well in this case, but the most famous one is the Hadoop Yarn. Spark components at a higher level. You have Spark SQL, that's more of like an interactive queries. Spark started for batch processing at the beginning, replacing Hadoop MapReduce workloads. Now kind of moved into a Spark streaming, especially with the IoT sensors and even log data coming in from different servers and even social media networks data coming in at a faster rate. So Spark is capable of capturing that and analyzing that and producing insights from that. Spark MLlib, it's primarily for the machine learning aspects of it. So when you want to run large machine learning algorithms in a distributed fashion, Spark MLlib provide the optimized solution. And also you can have something called graph. So graph is it's a vertices and edges where you can represent your data and then quickly, easily find out the relationship that you can't really see it in any other data format. Spark Core Engine sits at the bottom, and the cluster manager like Yarn or Mesos works with your client programs in terms of how you want to get access to the resources. At the bottom is the HDFS, so you can put your files in HDFS, or in this case, if you're going with the cloud, Azure Blob Storage or a data lake store is an excellent option too. So ingest your data, process it, and then write back the results back into the same data store. At a very high level, Spark works on 3 different objects: data frame, data set, and RDD. We briefly touched on RDD. It's a resilient distributed data set. That's the fundamental to the Spark paradigm. everything at the end boils down to RDD. These data frames and data sets are higher level APIs, and RDD is the lower level APIs. If you are, you can choose to work with any of them, and there are some pros and cons, but everything boils down to RDD at the end. And we will spend some time on understanding how this RDD works. Then data frames are available in Python and Scala. The data set is available only with the Scala. It's mostly compile time type safety that provides in data set, and knowing that Python is not a compiler, it's an interpreted language, so it's natively not supported. So data frame does the job for us. RDD is a distributed data abstraction. It is resilient. When you create a data set, when you submit data into create an object called RDD, so the underlying data lives in different nodes in the cluster. And we talked about a little bit ahead the challenges of distributed computing. When you have multiple nodes, the chances of something goes wrong, or the failure, hard disk or network failure, is very high. That's where you would want to make sure that you are not losing the data. So the cluster manager and the master program works together in identifying where the replica of that data is available, and immediately bring that node into action and shift all the jobs to that node and continue with that. So at any point of time, you will not lose your data, and it's very resilient in that case. Immutable. Once you create an RDD, you cannot change it. You basically destroy it. When you do the transformation, you are basically creating a new RDD. And it is, of course, very much useful for structured and unstructured data as well. There's something called a lazy evaluation. That's the framework that Spark uses in terms of understanding what you are trying to do. Based on that, it generates the most optimized plan. So when you execute a command in Spark, there are two types of command that we will be using. One is transformations and actions. Spark doesn't really do anything. It completely waits for you to come up with the action query, then it goes and finds what is the optimized execution plan for what you're trying to do. For example, like you're doing some transformation and then you're issuing a filter command. So Spark understands that you are filtering at the end. Meantime, it will go and filter all those data at the beginning and then do all the transformations after that. So that's one of the things that it makes it easier and faster than Hadoop framework. Not only it does everything in memory, but it comes up with this more optimized execution plans. That's where the lazy evaluation comes into play. Why do you want to use RDD? It's a low-level API. If you want more control, more flexibility, that's when you would want to use RDD. Otherwise, data frames are much faster, highly performant, so you could continue to use data frames in Spark than RDD. But the RDD is the fundamental to everything when it comes to the objects that are in play. You can do a narrow transformation or a wide transformations, and you can also do actions. So those are the kind of operations that you do in RDD, which are kind of applicable to data frames as well. So some of the examples of narrow transformations and wide transformations are like map, filter, flat map. It basically goes back to our MapReduce framework. Your maps are pretty much transformations, and actions are reduce, collect, all the aggregate functions. Those are their actions operations. So this is not a full list. In fact, if you go to the Spark website, so you will see all the latest one, and of course they keep adding more efficient operations as we speak. Narrow versus wide transformation. So when you store an object, when you store the data, so it gets created into multiple machines, and each machine have partitions, map, filter, union, those kind of simple operations called narrow. In this case, the data in each partition of the parent RDD on the left, like the blue color is the parent RDD and the orange or the yellow color is the child RDD. gets created after the transformation. So let's say you apply the map function on the left. So each of that will come into play when it comes to creating a new RDD. So parent RDD is used at most one partition of the child RDD. So there is it's a easy data transfer from one RDD to another RDD. So it's called narrow transformation. Contrast thing is on the right side. So you have the wide transformations where the data from one partition in your parent RDD going into multiple partitions in the child RDD. So basically the complex functions like group by are the classic example of this wide transformation. So the data transfer between the nodes and between the partitions are high, and those are more expensive operations compared to map, filter, unions, or the simple joins that you see on the left. So earlier we saw how we do mapper function, reducer function, combiner function, sorting using Hadoop MapReduce framework, where you had a Hadoop streaming job. Then you have to write a mapper function separately, reducer function separately, even for a small use case like counting the words. It can be done very simply in Spark. It's an equivalent example of how it is done in Spark. You simply use the map function and the reduce function. Just you operate them on the RDD that you create. So that's how simple it is. It's not just the execution is faster, even writing a program is also very simple in this case. We will not be able to have time to do a DLAB. I quickly want to jump to data frame. Data frame is the advanced API built on top of RDD that we briefly discussed. It comes with two different engine on top of that called Catalyst and Tungsten. Catalyst is the it's basically an execution. Tungsten is the execution engine, and Catalyst is the optimization engine, query plan engine. So it does all sorts of more optimized plan based on the query that you write. Also, it provides Spark SQL capabilities. Like if you are coming from a SQL background, you'll be able to write transact SQL syntaxes the way we used to do that on the relational databases in the past. So it's pretty much same as that. And you could do all sorts of operations like map, reduce, everything just using SQL statements. So that's where the flexibility comes into a play. You could use again Python, Java, Scala or R programming when it comes to Spark SQL. So what you see on the top is using RDD, and what you see on the bottom with the select department average from table P data group by department. So basically it's the SQL syntax to do the same thing. Internally, it converts them into RDD and uses the Catalyst and Tungsten engine to execute faster. So data frames are much faster, but if you want to know the internals and understand the fundamentals of what happens behind the scene, I think having the understanding of RDD will be a major advantage for you in terms of writing more efficient queries even in the data frames. Whether it is RDD or a data frame that you are using, you could do lots of joins, inner join, left outer join, right outer join, full join, and Cartesian joins. In the case of data frames, you have not in capabilities when it comes to filtering out right anti and left anti join. That's not available in RDD. That's available only in data frames. So think of that as the filter rather than just joins. RDD or a data frame, they use internally the shuffle hash join. It's kind of an equivalent to the shuffle and sort that we have seen in the MapReduce. So your table 1 and table 2 are your base RDDs, and when you do a map program, map function on top of that, and then do the reduce, it basically does the shuffle hash join to execute the similar capabilities that we saw in the MapReduce program. That's it. And there are some challenges in terms of how you handle if your partitions are too big or too small, uneven sharding. How do you make sure that you have a more efficient code In the case of unbalanced data, that's when you have data, like for example, some data based on the different states in the United States, like California has a lot more data than Rhode Island. When you have data like this, when you partition data based on the states, the small state data frames, you can broadcast that to each node in your cluster so that the data doesn't get shared or the crossed between the clusters nodes when you do the join with them. It's okay to distribute the data, the replica of the entire data into each node, so that avoids the trips between the nodes when you are joining with the small data sets. Think of that as like, if you have a master data, which is small in nature, but your transaction data are distributed in different nodes. So you can replicate this data into each of the nodes so that the join happens locally, so that you're not penalized for the disk IO. Something called broadcast is the key to do that. So different type of join. On the left, join on how it does. So in this case, we have the shuffle going on between this California data and the rest of the world data. All we are saying is that if you are joining again two different data sets, and if you're doing a filter, you do the filter first before you do the join. Those are some techniques that you would use when it comes to distributed computing. And this is the broadcast hash join that we briefly talked about earlier. So that's pretty much, I think, when it comes to data frames in RDDs and how we use them in Spark. Just wanted to compare the speed at which data frames can work versus RDDs. Data frame Python and data frame Scala, even though it doesn't show much difference, I would still recommend using Scala for your production load. But when it comes to testing, experimenting, proof of concepts and things like that, you could pretty much use Python. And you have R and SQL is also available. So it's a very, very high level overview of how the distributed computing framework worked, the MapReduce paradigm, and how Hadoop started with that, and some of the challenges that we faced in Hadoop, and how Spark overcame with the invention of a resilient distributed data set, and then the advancement of data frames on top of the RDD.
We are Starweaver, education you can bank on. For more information, contact us.